Hi, so this is a bit late, but welcome to lecture 3, maybe? Okay, so I have to get this out as quickly as possible because the TAs will go over it in the tutorial tomorrow. So today we're going to cover asymptotic notation, which is known as big O notation by most people, but that's because they only use big O, whereas asymptotic notation actually takes in other symbols, which we'll see today, which are like big O, but flipped, and big O, big omega, little omega, and theta. Most people only use big O. Most people are only really familiar with big O, or they will have learned the others in school. They don't use them, and they use big O improperly in cases when it shouldn't really be used. I'll explain that. You shouldn't do that because now you will see why. Okay, so the idea behind big O. Actually, I'm going to push this back a bit. Just a bit. The idea behind big O is when we're analyzing, actually, we didn't come up with big O, mathematicians did. Because they want to be able to talk about functions without worrying about irrelevant stuff. So if anybody's seen, for example, Stirling's formula for approximating factorials, then if you look at it, it's got like, okay, well this it's more or less the n factorial is equal to this, plus some other what's called lower order terms. It means that asymptotically these are irrelevant. If you get this part right, you're like almost all the way there. So, why did we adopt this? Well, we like it because a computer, if you implement your program, and you implement it in C or you implement it in Java, this will mean it runs slightly differently. Also, if you implement it on slightly different architectures, this means it runs slightly differently. Different models of computers, whether or not there's something else, various constraints, there's something else running on the computer. Now that can actually slow things down quite a bit. But generally, you want to be able to talk about sort of a high level, you want to be able to compare two algorithms without talking about like who coded them, what language are they coded in, what machines are they running on, that kind of stuff. So all of that, assuming that your programmer is not really bad, will not make more than a constant factor difference. If I hire an expert programmer, maybe it will run 5 times faster. If I hire, if I spend a lot of money on a very fancy computer, maybe it will run twice as fast, maybe it will run 3 times as fast. If I use C instead of Java, maybe it will run 50% faster, whatever. All of this is really constant factors. But we don't care about that, because we're designing the algorithm. We're not interested in programming. That's not what this course is about. We're interested in comparing difficulties of problems and efficiencies of algorithms. So we don't want to consider these stupid little constant factor things. Now, okay, out in the real world, constant factors make a big difference. But for algorithm analysis, you don't want to worry about them too much. You don't want to cheat by like, we managed to say, for sufficiently big input, and then you have some huge constant factor which you know is there and you deliberately ignore. Well, sometimes you cheat. It depends on whether or not you ever actually plan to implement what you're doing. So we don't want to talk about constant factors. And we don't want to talk about what happens on small inputs, right? Because insertion sort will beat merge sort on small inputs, on things like five elements. No, you would never do a merge sort on that. You just insertion sort it. So we don't care about like how do the algorithms behave on really small inputs. And the reason, so we want to say, on big enough inputs, how do these behave? Now, big enough is a very flexible term, because what was big enough when I first started programming is absolutely tiny now. So you want big enough to be like, yeah, okay, if I make a statement about how these algorithms compare, I want it to be true now, and I want it to be true in 20 years when the memories are 100 times larger. So big enough should be, elastic. So we want to be able to say things like, this algorithm A is faster than algorithm B, or, it's, except maybe for constant factors and for sufficiently large inputs. So now, in particular, we want to say if we have a function that bounds the time that algorithm A takes, and a function that bounds the time that algorithm B takes. So let's say that algorithm A takes f of n time, and algorithm B takes g of n time. Then how do we say this thing about like, except for constant factors and for sufficiently large inputs? Well, we're going to want to say something like, so, f of n is at most a constant factor times g of n for all sufficiently large values of n. Okay? So, that sounds kind of mathy, but this is what we want. I mean, I hope you understand, since this is not an interactive session, I hope you understand that this is something you'd like to be able to say, my algorithm is at most a constant factor times this running time for all sufficiently large values of n. Okay? So this is like, yeah, okay. My algorithm runs in n log n time, except that I have to set up this big table at the beginning, and so it doesn't run in n log n time for n less than 100. But we don't care. Still, we want to say it runs in n log n time. Okay, but that's not true, so instead we want to say that it runs in some, like a constant factor times n log n, at most a constant factor times n log n, for sufficiently large values of n. Okay? So let's write this in sort of a slightly more mathy way. So let's say that there exists a value n sub 0, actually, sorry, there exist values n sub 0 and c, and these are, or actually, let's, instead of even saying values, let's say constants. Such that f of n is less than or equal to c times g of n for n greater than n0, right? Okay, so why do I want this to be constant? Because I don't want these things to be like some function of n or something like that. Right? So there's going to exist a value n, n0, and c, and c can depend on how you choose c could depend on how you choose n0. Maybe if you say, okay, I want my n0 to be 100, c might have to be bigger. If you want n0 to be 1,000, then you might be able to choose C small. You don't actually have to care, because you don't care what these are. You just care that they exist, right? So now, for all sufficiently large values of n means for all values n greater than or equal to this constant n0, which you don't have to specify particularly. Okay? So let's just patch this up. There exist constants n0 and c such that f of n is less than or equal to g of n for n greater than or equal to n0. Okay? So, this is equivalent. So now, let's talk about, we want to say that some function, this is true of some function. But what we can do is consider the set of let's make this even more mathematical and say, consider the set that was an ugly curly brace. H of n, so it's a set of functions such that there exist, this backwards E means there exists. There exists n0 and c such that for all, this upside down A thing, actually it looks like more like a wedge. This line is curved instead of straight, I think. So it's not exactly an upside down A, but close enough. Such that for all n greater than n0, we have that h of n is less than or equal to c times g of n. Okay? Now, we'd like to be able to say, so if I want to say this, fn is the most constant function factor times g of n for all sufficiently large values, then what I can just say is that f of n is in this set. Okay? So this set has a name. This set is called O, big O, G of n. Okay? Big O, G of n is a set. Okay? It's not itself a function. Okay? It is not a number. It is a set. So, let's just move this over. Let O of G of n be defined this way. So now this statement, we can say that very easily by saying f of n is in O of G of n. Now a lot of people don't write element here. This means in, right? This means is an element of. They write equals, okay? Which is, you get used to it, but from, strictly speaking, is horrible, because equals, equality relations are transitive, reflexive, and symmetric. So in particular, that means that if A is equal to B, B is equal to A. But that's not true for example, we could say n is an element of O of n squared. Okay? Or we could even say 100n is an element of O of n squared. Because this set, O(n) squared, is the set of all functions such that there exists some constant n0 and c, so blah, blah, blah. So is this an element in there? Yes. Why? Well, for example, I can choose n0 equals 101 and c equals 100. And then, well, actually, I can even choose c equals 1 in this case. No, let's say I'm going to choose, okay, this is like what I did in the Collaborate Ultra session. I choose n is equal to 60 and c is equal to 2, just to make it a little bit more interesting. So then I have 100n on one side, and so for any n greater than 60, this side is 100n, and this side is 2 times n squared, which is, so n is at least 60, so this is greater than or equal to 2 times 60 times n, well actually because it's greater than 60, is actually strictly greater, and so this is 120n, which is bigger than 100n, for n greater than 60. I mean, in order for it to be less, n has to be negative, which we don't want to think about here. So, this is true. If I were to write equality, and we were to consider it's symmetric, we would be tempted to conclude that n squared is in 100n. N squared is an O, big O of 100n, which it is not. Okay, why not? Because for any c you might choose, for any constant c you might choose, for sufficiently large n, you cannot choose an n0 and a c, because for sufficiently large n, pick a c, pick some constant c. For sufficiently large n, n squared is going to be larger than c times 100n. Okay, so let's pick a c. Let's pick c is equal to 90. So let's say c equals 90. Then on this side we have n squared, and on this side we have 90 times 100 times n. Okay, so what I'm going to do is consider n larger than 900 and, well, strictly larger than 9,000. Strictly larger than 9,000. So this is going to be n times n. So this is going to be greater than 9,000 times n, whereas this is actually going to be 9,000 times n. Okay? So this is not true. So that's why, maybe just for this class, we're going to try to avoid using equals. There are a lot of other things people will do to abuse asymptotic notation. Get used to them. It's like people not being able to use apostrophes correctly. You sort of know what they mean, and it just makes you sound very picky if you correct them all the time. You may be right, I mean you probably are right, and they're probably wrong, but this is, notation is like language, it's mostly about communication. Now if you're doing something important, you should get it right, okay? Whereas if you're just out and you're in a lecture and you hear somebody say something and they write equals, do not stop them, okay? It will make you unpopular. Except with people who care. Okay, so this is what we need. Okay, so there are lots of tricks for showing that some function is in big O of another function. Okay, So they're in the book, they're on the internet, they're in all kinds of courses. I will post notes. But for today, because I want to do this half of the lecture, I want to get through a bunch of other stuff. I'm going to let the TAs cover it tomorrow, and I'm going to let you read about it on other places. Okay? So I'm just going to note one thing that's useful to know is that there are functions such that f of n is not in O of g of n, and g of n is not in O of f of n. Okay, for example, n to the, and this might be a bit small, make it a bit bigger. Consider for integers, you have n to the n mod 2. So for n equals 0, this is 0 mod 2, which is 0, which is, so this is 1. And then you have n to the 1 mod 2, which is n. And then for n equals 2, this is 2 to the 2 mod 2. 2 mod 2 is 0, therefore 2 to the 0 is 1. And then it's n is 3, this is 3 to the 3 to the 3 mod is 3 to the 1. And then 4 to the 0. And then 5 to the 1, and then 6 to the 0. And 7 to the 1, okay? So it's going 0, 1, 0, 3, 0, 5, 0, so it's bouncing up and down, okay? And then consider n to the n plus 1 mod 2. Okay, so what does this do? For n equals 0, it's 0 mod 2, which is, oh, no, actually, sorry. 0 to the 0 probably isn't defined. Forget this. Okay, so this was, we're going to start at 1. 1 to the 1 mod n is, okay, we're going to start, forget this bit. Okay, so 1 to the 1 plus 1 is 0, so this is also 1 to the 0 is 1. Okay, now 2 to the 2 plus 1, this is, 2 plus 1 is 3, mod 2 is 1, so 2 to the 1, this now goes 1, 2, and then for 3, this is 4, so this is 0, so it's 3 to the 0 is 1. Yeah, actually, let's say that this is... Okay, so what are we going to say? This is going to be... I got this figure slightly wrong. But you can see what's going to happen. It's going to bounce, and it's going to bounce up when this one goes down, and down when this one goes up. Okay, so strictly speaking, I got the figure slightly wrong, but because this level should be, it doesn't go down to 0, it goes down to 1. Yeah, whatever. I'm not going to re-record this lecture because of that. And apparently you have to pay and buy some super fancy software to be able to pause these things. So, no. Okay, so it's just important to know that just because, so this means sort of asymptotically this is bigger than this. It's not always true that either A is bigger than B or B is bigger than A, or they're about equal. It's because in the case of functions, it can be A is bigger, now B is bigger, now A is bigger, now B is bigger, right? Okay? So you can have this case where we cannot compare with big O notation. Now I have 20 minutes to tell you about the other functions in sort of the same family as big O, the other symbols, not functions, but symbols in the same sort of the same family as big O. Okay. So what we're going to do, because we don't have a big enough whiteboard, we're going to write O of G of N up here in small letters that I hope you can still read. There exists N0 C such that for all N greater than N0, H of N is less than or equal to C times G. Okay, some people actually write the positive constant part where they say N0 and C are greater than 1, are greater than 0. That's implicit. Think of me writing that, but possibly I would if I had more time and a bigger whiteboard. It does actually matter later, in some cases. Okay, so now what you get people saying are things like, so this is mostly a repeat of what I said in the Collaborate Ultra, which you can access through Collaborate Ultra, through Brightspace. People will say things like, my algorithm takes O and log n time. Okay, so now we understand what this means. It means that my algorithm takes some function f of n. The time it takes on an input of size n is f of n. Let f of n be the worst case time it takes on an input of size n. Okay, so we could even say in the worst case. So this means that there does not exist, when I say in the worst case, there does not exist an input of size n for sufficiently large n. I mean, if you consider, if you say, okay, g of n is the time it takes for the absolute worst instance of size n, then g of n is in O n log n. Okay, so you can say my function, my algorithm takes. Why did I say g of n? Okay, my algorithm takes, if g of n is the if f of n is the time, the most time it ever takes on an input of size n, then you're saying, okay, f of n is an O n log n. Okay, so now we understand what this means. It means that there exists an n0 such that for inputs of size larger than n0, so there exists an input, an n0 and a c such that for inputs larger than n0, f of n is bounded by c times n log n. Okay? And then they will say, your algorithm takes O of n squared time in the worst case. Therefore, my algorithm is faster. Well, they may say faster, or they may, if they're being picky, but still not correct, they may say asymptotically faster. Why is this wrong? Okay? Why Why can you not say this? People do say this. You will hear people say things like this. They will say insertion, merge sort takes n log n time in the worst case. Insertion sort takes order n squared time in the worst case. Therefore, now this happens to be true. Therefore, merge sort is faster. Yeah, okay, that's true, but it doesn't mean that their reasoning is correct. Is faster than insertion sort, because you could also turn around and say, okay, well, heap sort takes order n log n time in the worst case. Merge sort takes order n squared. Yes, that's true. Okay? Therefore, there exists an n0 and a c such that the time that merge sort takes for n larger than n0 is bounded by n squared. Yes, it's actually bounded by n log n, by c times n log n. So yes, it's automatically bounded by c times n squared. So this is true. I mean, so if you translate this back into words, what they're saying is my algorithm takes at most this much time, possibly multiplied by a constant factor for sufficiently large values of n. Your algorithm takes at most a constant factor times n squared time for sufficiently large. But that at most, it's like if I said, you know,